photons.
So thank you to the organizers for giving me inviting me to this workshop. So I will be quickly trying to review new physics searches with CMS, of course, not all of them because this is hundreds of papers, but those which are relevant to the topics of this workshop. Okay, I'll start with a very generic first slide. Of course, CMS is a versatile detector, so we have many opportunities for new physics searches, thanks to the rather large rapidity coverage and excellent energy and momentum resolution, and also large data sets for several collision systems. So on the left, I put a table with the heavy ion data sets that we have in CMS. In particular, I highlighted in red the latest one, which is lead in 2018, and so which is a bit less than 2 inverse nanobarns. And then I also put in the last column the scaled luminosity by A squared, which is at least for anything which is initiated by hard patterns, the equivalent PP luminosity, which, as we can see, is still quite low for this. But then, of course, this scaling does not apply to things which are initiated by photon collisions, photon interactions. And then on the right, this is the integrated luminosity for PP collisions. And so we are at 180 inverse femtobarns since the start of the LHC if we combine run 1 and run 2. Okay, so this is the outline of the talk. So I'll be starting with ALP search in LEDs, covering much less detail than Christophe, but just yeah, a reminder about what our results in CMS. Then one word about magnetic monopoles. We don't have a result yet in CMS, but I'm just going to say a few words. And then also I'm going to quickly review some of the results we have in PP, in particular on ALPs and magnetic monopoles, well, mostly ALPs actually, and also a few words on long-lived particles. Okay, starting with ALPs. So we've seen these diagrams already, and the motivation. So I think I can go quickly on this slide. So of course, the advantage is that we have these very strong electromagnetic fields in latent collisions. So this process will be enhanced compared to PP. So in this paper, which CMS has published, the strategy was to normalize the light by light scattering process to photon-induced electron pair production, which has a much larger cross-section. And then, yeah, we can also use the same final state for looking for ALPs. Okay, so these are the data. So here a reminder of the cuts that are applied in this paper by CMS. So by the way, this is using 2015 LED data. So this is less data than what was shown by Atlas. The analysis of the full 1.2 is ongoing in CMS. So cuts are written here: photon energy, transverse energy above 2 GeV, pseudo rapidity below 2.4. The mass is above 5 GeV of the diphoton system. PT for gamma gamma is below 1 GeV. And the ecoplanarity below 1%. So data are consistent with signal plus background expectations. And we achieve about 4 sigma evidence using this data. And the measured cross-section is written here within the fiducial cuts, which are the ones mentioned on the slide. So ecoplanarity is on the left. Of course, we see that the signal is concentrated at, I mean, this corresponds to back-to-back photons, which is a phi of 0. And then on the right, if we only focus on well, this first means, and applying this coplanarity cut here. This is the invariant mass distribution of the diphotons. And this is what we'll use to set limits on ALP production. So basically, the point is that we will be looking for a resonance in this diphoton spectrum. And these are the limits that we get on ALPs. So the graph on the left here is the upper limit on the cross section for gamma gamma to an ALP decaying to gamma gamma as a function of the ALP mass. And then these are the kind of constraints that we get in this plane of coupling and ALP mass. The limits from this paper are in green, and the observed one is the solid line. So at the time of the publication, these were the best limits from 5 to 50 GeV for a coupling of the ALP only to the electromagnetic current. And if we allow a coupling to the electroweak current, then these are the best limits between 5 and 10 GeV. And so this was recently improved by Atlas, though we still have the best limits in CMS between 5 and 6 GeV, but above this, Atlas has a lot more data, so they get better limits on ALPs. Okay, so that's it on ALPs. Let me move to magnetic monopoles. So as I mentioned in the beginning, we don't have a result yet in CMS, but still I thought I would discuss it quickly. There will be some talks more specifically on this, and I'm not really an expert, but I just want to, well, I'm going to say this quickly, that this corresponds, such a signal would correspond to unique signatures experimentally. So first, the trajectory in the tracker is non-helicoidal because of the magnetic charge. Also, such a particle would be heavily ionizing. So we would see it if we look at the charge deposited in the detector, in particular in the tracker, we would see difference with standard model particles. Also, we expect a specific shower shape in the calorimeters. And if we consider monopolium, which is a bound state of two magnetic monopoles, then this could decay to diphotons, and we could also look for resonance in the diphoton spectrum. We did some preliminary studies in CMS. Of course, one question is whether we can do something which is competitive with MEDAL. So there will be also a talk from this experiment later, which is dedicated, is dedicated to this kind of signals. So a very naive estimate that we got for what we can do in CMS was a lower limit of 400 GeV, which is much lower than the recent results from MEDAL. So this was with a production model. The production was modeled using Supercheck 3. That was, just a preliminary study. So we focused on looking for large clusters in the tracker. So we focused on this second unique signature with the fact that magnetic monopoles are heavily ionizing. So of course, this first study has a lot of places for improvement. We should include the other signatures for better sensitivity. On the other hand, this was a naive study. We did not include systematic uncertainties. So that's why this should be, taken with a lot of care, this number. But I think what we can say is that which experiment to use and also which system. So this number is considering lead collisions with, I think that was with the 2 inverse nanobands that we got in 2018. Which is best is not just, maybe there is not a single answer because different models exist for the production of magnetic monopoles, and depending on the model parameters or which model you use, it could be that the answer is different. So, you know, at some point it could still be interesting to do an actual analysis in CMS. And so, yeah, there will be a lot more information in the dedicated talks on this topic. And so finally, I'm going to move to PP, which is not the topic of the workshop, but I'll cover the kind of exotic signals that are discussed in this workshop. So I start by mentioning that, yeah, obviously exotic searches is a very major topic in CMS. So this is, for instance, the number of publications by the collaboration in different physics working groups. And you see that the largest working group is for Exotica, so yeah, exotic searches with almost 200 papers. And then if you include also these other groups like supersymmetry and this beyond 2 generations, which is looking for yeah, new generations of quarks or resonances or leptoquarks and so on, then you get to like almost 400 searches, which I'm not going to cover anyway. I'm not really an expert. And this is also like an overview of the kind of constraints that are available from CMS papers. I'm going to focus on ALPs and long-lived particles, which are going to be discussed in other talks in this workshop. So starting with ALPs, so there is only actually one paper, so apart from the one I mentioned in LLED, so only one paper in PP explicitly setting limits on ALP models, which is this one, looking for the WWW final state. And so this is looking for WA and then A decaying to 2 W bosons. References here. And these are the limits which are set. And then I'm going to talk also about diphoton searches. So we have a few papers on this, but none of them is directly targeting at ALPs. They are looking for the models for particles decaying to 2 photons. And so, yeah, about magnetic monopoles, there have been some studies inside CMS, but we don't have results yet directly looking for magnetic monopoles. So maybe at some point in the future.
5 minutes left.
Okay, good. Okay, moving to diphotons. So as I mentioned, several diphoton searches were published in CMS, covering a wide mass range between 60 and GeV and 4.5 TeV. So all of them are, you know, as usual, looking for bumps in a diphoton spectrum. For instance, the one on the left is looking for, this is a paper which is looking for additional Higgs bosons decaying to gamma gamma or any new resonance. This is between 60 and 120 GeV. And then this graph on the right is from a paper looking at the high mass end of the spectrum, and again looking for any resonance there. And this is one example limit on you know, any model which would predict a new particle decaying to 2 photons. So as I mentioned, this is not directly setting limits on ALPs, but several publications are available which are reinterpreting these results in terms of ALPs and putting them in this plane with the ALP mass and coupling. I'm putting 2 examples here, and a few examples of papers are listed here. And I'll finish with a few words on long-lived particles, again, which this topic will be covered in more detail later. So just a short introduction here. These long-lived particles, they correspond to unusual signatures that require innovative techniques. And this corresponds also to an array of challenges to overcome experimentally. So there are some atypical, meaning non-collisional backgrounds. This requires dedicated physics, object ID, and reconstruction, and also triggering on some weird or low energy signatures. But there is a large number of possible long-lived signatures and strategies. And here an example of the kind of signatures that we are talking about. So we can look for, okay, maybe I don't have to list all of them, but this involves all of the detectors, the tracker, the calorimeters, also the muon stations. We can look for this very displaced particles, displaced jets, and so on. So this is a recent summary of the status in CMS for a few models. So the x-axis is the lifetime of the c tau of the particle, and for different models. So R parity violating SUSY or conserving in yellow, and then other models in green. I'm just showing here one example, which is for gluinos. And I'm showing this plot because this is combining 3 different searches, different papers. And we see that with different strategies, we can be sensitive to different ranges of lifetimes. For instance, we have here displaced vertices for the shortest, like a few millimeter up to centimeter lifetimes, c tau, and then displaced jets for a bit larger lifetime, and then for the longest ones, they are looking for delayed jets. And okay, I'll finish with this very simple summary. So we have a lot of BSM searches in CMS with PP data. Only one, I think, so far with heavy ion data, which is this ALP search in lead-lead. But obviously, we have opportunities for more, for instance, like magnetic monopoles, or all the things that you know.
Thank you. Thanks a lot. So comments, questions. I see 2. Wendy first, and then Artu.
Hi, thanks for that nice talk. I just wanted to point out a couple of things. One is that Atlas has published 3 searches for magnetic monopoles in proton-proton collisions. And the other thing is that the Atlas results are they're better than the metal results, in the sense that we have better sensitivity for the charge, basically 1 and 2 times the fundamental magnetic charge. So I hope people remember that Atlas is still in the game for magnetic monopole searches.
Good. And just to confirm, so all of these 3 papers are using PP data, I guess.
Yes, yes. There has not been any heavy ion search yet. There are some studies that are being done to see if that can be, if that's possible well, basically we're looking at UPCs. Now you mentioned a number like 400 GeV. Was that for, not for the UPCs, right?
I think this was photon-induced production. But again, this number, I'm not so very confident. I would not publish it, so.
Fair enough.
Thank you. Artu.
Hi, thanks. Really nice talk. So yeah, I actually wanted to ask about the same thing, where the 400 GeV comes from. So you said photon induced. So do you mean just like a Grelian kind of a production process, or what's the kind of process that that number is based on?
What do you mean? You mean, yeah, what's the process exactly that we considered?
That's right. So, because obviously in order to get a mass bound, you need some kind of calculation of the cross sections from some process. So is that, what is the production process that is based on?
Yeah, I think this is what I used anyway. We use the model which is implemented in Superchick.
Yeah, so
I need to actually I need to double check the details.
Yeah, I'm just not familiar with Superchick, but anyway, yeah, I can have a look at that as well. So thanks.
Okay.
Thank you. Now, Albert, please.
Hi. In fact, Superchick usually does kind of exclusive processes, but this is just a side comment for we use it for diffractive processes and so forth. So maybe it's that kind of thing, just to answer R2. But yeah, I know this generator. I just have to figure it back. It doesn't have monopoles, but something was put in for that. But I have a question to Émilien. For the exact on the monopoles, sorry, it's a monopole directed thing. I know particularly from the PP part that it's very difficult to do that in CMS due to the spikes which we have in the eCalculorimeter, which is coming from these backgrounds. But you do it here looking at ionization, you say, for tracks. I mean, this sort of rough study. But you know that you cannot do that with the standard reconstruction of CMS, right? Because these tracks are bending not in the R5 plane, but in the RZ plane. So they would not reconstruct, for example, in if you use a normal reconstruction.
Yes, so this is why in this case we were not even using tracks, but just looking for the clusters.
Just for hits with high.
Exactly, just hits.
Okay,
yeah.
Okay. Yeah, then I understand what happened. So you don't rely on tracks. That's fine. Okay, thanks.
Thank you. Anything else?